In this lecture, I will discuss solution to some specific problems from the exercise of the chapter number 5 from the Mechanics of Materials textbook by Beer and Johnson. The topic is analysis and design of beams for bending. The first problem which I have chosen is problem 513 from the exercise. Assuming that the reaction of the ground is uniformly distributed, draw the shear and bending moment diagrams for beam AB and determine the maximum absolute value of the shear and of the bending moment. Okay, here a beam has been given, beam AB, which is under two loads, two concentrated loads, each equal to 1.5 kilonewton at point C and point D, and the beam is resting at on ground. So ground is applying a distributed force. I want to change the color of the marker. So ground is applying a distributed force on the beam. Okay, we have to draw the shear force and bending moment diagrams first, and then determine the maximum absolute value of shear and bending moment. Before that, first we have to draw the free body diagram of this beam and find this distributed load which is being applied on the beam by the ground. I will draw the shear for the free body diagram here. This is the beam. A distributed load, upward distributed load, is being applied on the beam. Let us consider that this is equal to W, distributed load. At point C, there is a concentrated force of 1.5 kilonewton, and at point D as well, there is a concentrated force of 1.5 kilonewtons. Okay, the total length of the beam between A and C is 0.9 meters, sorry, 0.3 meters. Between C and D it is 0.9 meters, and between D and B it is again 0.3 meters. So it is a symmetric beam. Okay. Before everything, I want to convert this distributed load into a concentrated load. So the concentrated load will be applied at its centroid, and the total length of the beam is 1.5. The distributed load is being applied on the total length. So length multiplied by the distributed load is 1.5 W. Okay. Now I want to find this W first. Summation of forces in y direction is equal to 0. There are three concentrated forces. One is 1.5 W and two downward forces 1.5 kilonewton each. So W becomes 2 kilonewton per meter. W is distributed load. This W has been calculated now, and the unit of distributed load is kilonewton per meter. Okay, now we will section this beam at different points. Okay, I want to section this beam between AC, between CD, and between DB. So the first section I want is between A and C, then between C and D, then between D and B. Three sections. Okay. When we section it between A and C, section A to C, the beam will be like this. This is W, and the length of this section is X. X is between 0 and 0.3. Okay. If we convert this to, here will be a downward shear force and a moment. Okay. I'm calling it V1 and M1. Okay. Summation of forces. This distributed load is actually equal to a concentrated load of Wx. Total length is X and the distributed load is W. Summation of forces is equal to 0. So V1 becomes Wx, and actually W is equal to, W is equal to 2 kilonewton per meter. It will be 2x. Okay. V1 is 2x. Summation of moments is equal to 0. If I consider the counterclockwise moments equal to counterclockwise moments as positive, so m1 minus 2x into its distance, which is x by 2, is equal to 0. So m1 becomes x square. Shear force is a linear function of x and bending moment is a quadratic function. Bending moment will always be 1 degree higher than shear force. Okay. Next section is section C to D. Between C and D, section number 2. Again, I will draw the beam here. There is a force of 1.5 kilonewton at point C, and the beam is being supported by an upward distributed load of 2 kilonewton per meter. This total length is x. Okay, this distance is known to us. This is 0.3 meters. So this remaining will be x minus 0.3. Here is a downward force V2 and a moment M2. Okay. This distributed force can be divided into a concentrated, it can be converted into a concentrated force of 2x, and which has a distance of x by 2 from this end. Okay, summation of forces in vertical direction is equal to 0. So V2 plus 1.5 minus 2x is equal to 0. So V2 becomes 2x minus 1.5. Okay, summation of moments is equal to 0. Let me consider counterclockwise moments as positive. So there is m2 plus 1.5 into x minus 0.3 minus 2x into x by 2 is equal to 0. So m2 becomes, if we simplify this expression, it will be x square minus 1.5x plus 0.45. Again, moment is a quadratic function of shear force. Moment is a 1 degree higher than shear force. Shear force is linear and moment is quadratic. Okay, third section is between D and B. So I will section the beam again between D and B. I will draw the beam here. It is being supported by a distributed load. This is point A. At point C, we have a 1.5 kilonewton force. Then at point D, again 1.5 kilonewton force. This distance is 0.9 and the total length is x. This will be 0.9 plus 0.2, 1.2, x minus 1.2. Okay. Distributed load is 2 kilonewton per meter. Here is V3 and M3. Summation of forces in vertical direction is equal to 0. So we have V3. Okay, this distributed force can be converted into concentrated force equal to 2x. So V3 plus 1.5 plus 1.5 minus 2x is equal to 0. V3 becomes 2x minus 3. Similarly, summation of moments is equal to 0 if I consider counterclockwise moments as positive. So we have M3. This force has a distance of x by 2. M3 plus 1.5 into x minus 1.2 plus 1.5 into x minus 0.3. This force has a distance of x minus 0.3 from the from this end. Okay, and minus 2x into x by 2 is equal to 0. After simplification, M3 becomes x square minus 3x and plus 2.25. So we have derived expressions for shear force and bending moment in the three sections. Now we will draw the diagrams. Okay. Shear force diagram in kilonewtons. Okay, from section A to in section A to C, when x is equal to 0, V1 becomes 0. In this expression, if you put x equal to 0, V1 will be 0. And if you put x equal to 0.3, so V becomes 90, sorry, V becomes 0.6. 0.6. Okay, since this is a linear expression, so it will be straight line, linear line. Okay, if we move to the second function here, where x is between 0.3 and 1.2, if we put x equal to 0.3 for point number C, if we put x equal to 0.3 in this point, in this expression, so V becomes minus 0.9. So previously at x equal to 0.3, V was 0.6. Now in the next expression at x equal to, because 0.3 is common here in section AC and in section CD as well. So here it becomes 0.9. So at point C we have two values of V. minus 0.9. Okay. Now, by putting this value 1.2, for each section we will put two values of x in the expression, the starting value and the end value. So by putting x equal to 1.2 in this expression, v2 becomes 0 plus 0.9. So here is at point B, x is equal to 1.2 and it is 0.9. This is a linear expression, this one. So it will be a linear line, straight line. Okay, again, in this last expression, if we put, this is when x is between 1.2 and 1.5. Okay. When we put x equal to 1.2 in this expression, v becomes minus 0.6. So again, at 1.2, it is minus 0.6. At point D, again, we have two values of v. One from section CD and the other from section DV. D is common between these two sections. And then at the end, when we put x equal to 1.5 in this expression of v, so it will be 0. From this expression, if we put x equal to 1.5, so v becomes 0. Again, the expression is linear. So here we got the shear force diagram. Now for the bending moment diagram, in kilonewton meters. In the first expression of m1, when x is between 0 and 0.3, when we put x equal to 0, m1 is 0. And when we put x equal to 0.3, m1 becomes 0.09. Okay, this is a quadratic expression, so it will be quadratic curve. Since the slope of the shear force diagram between A and C is increasing, so bending moment diagram curve will be counterclockwise. Okay, then for the next section, section CD, when we put x equal to 0.3 in this expression, again it becomes 0.09, which is the same point in this one as this one. And when we put x equal to 1.2 in this expression, 1.2 is at point D, so it again becomes 0.09. It shows it seems like the diagram will be like this line, but not. It should not be like this, because it is a quadratic expression. Sorry, moment expression. This one, we have kept these values of x in this expression to find 0.09 and 0.09. This is a quadratic expression, so we need to have a curve here. So for curve, I will put third value here between 0.3 and 1.2. The midpoint of 0.3 and 1.2 is 0.75. So I will put x equal to 0.75 in this expression to find the midpoint between these two. And if we put x equal to 0.75 in this expression, the moment will be minus 0.1125. Minus 0.1125. So it means here it is a curve. Okay, how we will draw the curve? If you see here, between these 2 points, the slope of the shear force is increasing. So I will draw a counterclockwise curve here. And then again, slope between these 2 points is again still increasing. So here another counterclockwise curve will be drawn. Okay. And at the end, in the last section, if we put x equal to 1.2 in the expression of moment, it will be 0.09, which is the same point in this one. And if you put x equal to 1.5 in this expression, the moment will be 0. Here it is 0. Again, this is a quadratic expression. So we have to draw a quadratic curve. And again here, shear force diagram has an increasing slope, which will be a counterclockwise curve. This is bending moment diagram. Now, in the problem statement, we were asked to draw shear force and bending moment diagram. So we have drawn shear force and bending moment diagram. Then we were asked to determine the maximum absolute value of shear force and bending moment. So from the diagram, we can see what is the maximum absolute value of shear force and bending moment. For shear force, the maximum absolute value is 0.9. The maximum numerical value actually. Sign does not matter here. Absolute value means regardless of sign, what is the numerical value. So shear force is maximum. And maximum shear force is equal to 0.9 here or here. And maximum moment is 0.1125 kilonewton meter. So here we can write from the shear force and bending moment diagrams, V maximum is equal to 0.9 kilonewtons or 900 newtons. And maximum moment is equal to 0.1125 kilonewton meters or 112.5 newton meters. This value of moment is maximum value. We only need the numerical value. The sign is not important for us. The maximum value of moment has been calculated. Okay, I will move towards the next problem. It is problem 552 from the exercise. Determine the equations of the shear and bending moment curves for the beam and loading shown in part A, and for part B, the maximum absolute value of bending moment in the beam. So first we will find the equations of bending moment and shear force curves. Okay, expression for load is given to us. It is a sinusoidal expression. First we have to find shear force and bending moment expressions. So we know that shear force is integral of negative load and bending moment is integral of shear force. So here we have been given with the expression for load. So we can simply integrate it twice. With the first integral we will find shear force, and with the second one we will find bending moment. Problem 552. Load is given to us. W is equal to W naught sine of pi x over L. Shear force is equal to minus W, integral of minus W. It will be W naught sine pi x over L. W naught is constant. Sine, integral of sine is minus cosine. So minus and minus sign, they will become positive sign. W naught into cosine of pi x over L, and then divided by derivative of pi x over L. So derivative of pi x over L becomes L over pi. So this is integral. You know how to integrate the functions, specifically the trigonometric functions. Plus there will be a constant of integration C1, because we do not have limits here in the integral. So we have to add a constant of integration. Again, moment is equal to integral of V. So by integrating this expression, okay, it will be W naught L square over pi square, and integral of cosine is sine plus C1x plus C2. There is another constant of integration here. Now how to find C1 and C2? We have to apply boundary conditions. What are the boundary conditions? At point A, where x is equal to 0, there is no moment. There is a force, but there is no moment. So at x equal to 0, there is no moment. And similarly at point B, where x is equal to L, there is no moment. So we will use these two boundary conditions. For x equal to 0, moment is 0, and for x equal to L, moment is 0. So we will put if this is our expression 1 and this is expression 2, so put x equal to 0 and m equal to 0 in equation number 2. So we get C2 equal to 0. Okay, then put x equal to L and m equal to 0 again in equation number 2, because m is for equation number 2, moment. We get C1 equal to 0. So we have received values of C1 and C2. In this case, they both are 0, so we have simplified equations. In some other cases, they may not be 0. So by putting C1 and C2 into equation number 1 and 2, C1 and C2 in equations 1 and 2, we get V equal to W naught L over pi cosine of pi x over L, and moment equal to W naught L square over pi square sine of pi x over L. So this was the first part of the problem, to derive expressions for shear force and bending moment of the beam. And in the second part, we were asked to find the maximum moment. So for maximum moment, its first derivative must be equal to 0. For any function to be maximum, its first derivative is kept equal to 0. So if we keep the first derivative of bending moment equal to 0, the first derivative of bending moment is shear force. So here if we keep shear force equal to 0, W naught L by pi cosine of pi x by L. It means cosine of pi x by L is equal to 0 and cosine of pi x by L is equal to 0 when x is equal to L by 2. So from this expression we have found x equal to L by 2, and now we will put x equal to L by 2 in the expression of moment to find maximum moment. So the maximum moment will be m maximum equal to W naught L square over pi square into sine of pi by 2. And sine of pi by 2 is equal to 1. So this expression is simply W naught L square divided by pi square. This is maximum moment, and this was asked in the statement of the problem to derive expressions for shear force and bending moment and to find the maximum bending moment. Okay, the next problem to be discussed here is problem 104 from the exercise of chapter number 5. In part A, using singularity functions, write the equations for the shear and bending moment for the beam ABC under the loading shown. And in part B, use the equation obtained for moment to determine the bending moment just to the right of point B. Okay. First, in this beam, we have to shift this point force P from here to point A. So it will be P, but by shifting a force from its point of application, offset of its line of application, so it has to be replaced with a force and a couple system. So it is being replaced with a force and a couple which it is producing equal to PA. Again, this force P is being shifted to point B and it is also producing a couple PA. Okay, because the distance between this force and point B is A. Okay, the sense of the couple will be direction of the force. Okay. So there are reaction forces as well at point C and point A. At point C there is a reaction RC and at point A there is a reaction RA. So the reaction force RA and the force P at point A, they both can be added again after calculating both these values. First I will find the reaction at A. We will draw a free body diagram. Problem 5104. Okay, summation of forces is equal to 0. How many forces are there? Before that, I want to keep summation of moment actually. We do not need this force. This is at the end, at the right end, and for singularity functions, we do not need the force at the right end. This is not useful in our calculation. So I want to take moment at point C so that we do not need to calculate this force. Summation of moments at point C is equal to 0. Okay. How many moments are there? Here's one moment. PA. Then this force RA is producing a moment RA multiplied by 2A. Then this force P is producing a moment P into 2A. Then there's a moment PA again. And then this force P is producing a moment PA. Okay, so I will keep all these moments here. RA into capital RA into 2A, its distance. plus 2a plus p, sorry, plus p into 2a plus p into a minus pa and minus pa is equal to 0. Okay. If we simplify this expression, Ra becomes P over 2. Okay. So reaction force, which I have assumed to be upward, has become positive P by 2. Okay. Now I will draw a free body diagram here. Is Ra equal to P by 2, and here is P, then this PA moment at point A. At point B, we have a downward force P and a moment PA, and at point C, we have RC, and we do not need to calculate RC. At point A, we have two concentrated forces, so I want to merge them both, and then there's an upward force P by 2 and there's a downward force P. So if we add them, there will be a downward force P by 2. So I want to replace these two forces with a single force P by 2 by adding them both. Okay, now this is our free body diagram, and we have to write singularity functions. Okay, to write singularity functions for this diagram, v x minus v naught is equal to, we will go to the table. In the table, for a downward force P, the singularity function of shear force is minus P into x minus a power 0. For this downward force P, it will be minus P into x minus its distance from the right end was given to us. Here it is also a, x minus a power 0. What is V naught? V naught is the upward force at the leftmost end. So here we have a downward force P by 2. In this case, over V naught is minus P by 2. If it was upward, I would have kept it positive. Okay, instead of this, if I use another method for your understanding, I simply write here like this, and I write a singularity function of this expression, and this force P by 2. This force P by 2 is downward, so minus P by 2 x minus 0 power 0. And then again, this force P is equal to, a singularity function for this force P is equal to minus P into x minus a power 0. In this case, again, we will get a similar expression. Vx is equal to, x minus 0 will be x. It cannot be a negative number. So x is length, it will always be a positive number. And any positive number minus 0 will be the same positive number. So x power 0 is 1. So I can write it as P by 2 minus P into x minus a power 0. This is singularity function for the shear force. For bending moment, I will write singularity functions. One method is to write initial condition here m naught, which is equal to pa. But some of the students have confusion in this method, so I will not write here any initial condition. I will write a singularity function for this moment. This moment pa, we will go here, singularity function for moment, for a concentrated moment here, it is equal to, okay, remember that this is a counterclockwise moment, this one. For a counterclockwise moment, bending moment function is, singularity function is minus m naught into x minus a power 0. In our problem we have clockwise moment, so we will use a positive sign in our case. Positive sign with moment into x minus a power 0. So here moment is pa, it is clockwise, so it will be positive. X minus 0 power 0, it has 0 distance from the left hand. And for this moment pa, again plus pa x minus a power 0. Okay, then we have two concentrated forces, p by 2 and p. For concentrated force, here we have bending moment equal to minus p into x minus a power 1. For downward force, they are using negative sign. We also have downward forces. Minus p by 2 into x minus, it has 0 distance from the right, left hand, so x minus 0 power 1 minus p, and it has a distance of a from the left hand, so x minus a power 1. We have used this expression. Okay, after simplification, here the bending moment will be, okay, this pa into x minus 0 power 0. X minus 0 is x and x power 0 is 1. So it becomes pa. Okay. The next function is this one again. This is p by 2 into x minus 0 power 1. X minus 0 is x and x power 1 can be written as x. Minus p by 2 x. And the other two functions will be the same as they are, pa into x minus a power 0 minus p into x minus a power 1. So this is our expression for the bending moment, singularity function for the bending moment. Okay, this is first part of the problem, to derive or to write the equation for shear force and bending moment using singularity function. The last part is use the equation obtained for moment to obtain the bending moment just to the right of point B. Just to the right of point B. Point B is at x equal to a. Just to the right means x greater than a. Okay, we will put x equal to a in this expression. Just to the right means almost point B, but x is a little slighter greater than a, so x minus a is a positive number. So in this expression, in the expression of moment for part B, up till now we were solving part A. So for part B, this is equation number 1. Put x equal to a in equation 1. Remember that x minus a is greater than 0. X is almost equal to a, so it means x minus a is 0. But if the point is a little at the right of the point B, little right of the point B, x equal to a till point A, so little right means it is slightly greater than a. So the difference of x minus a will be slightly greater than slightly greater than 0. So okay, it means if we put x equal to a in this part, in this term and in this term, they both are positive. So if they both are positive, it means they are not equal to 0. They exist here, and we cannot omit them. Okay, we cannot neglect these functions. But x is almost equal to 0. If x is almost equal to 0, so this is uh, almost a minus is almost equal to 0. Okay, m of x is equal to pa minus p by 2 into a plus pa into a minus a power 0 minus p into a minus a power 1. Okay, this term a minus a power 0, because this is a slightly higher than 0 number, almost equal to 0, a minus a in this case is almost equal to 0, power 0 is 1. So pa minus p by 2a plus pa into 1 minus this one, this is a minus this one, p into a minus a power 1. A minus a is almost equal to 0. It is not exactly 0, but almost equal to 0, slightly greater than 0. We will consider it as 0. So 0 power 1 is 0. After simplifying this expression, moment at point B will be, this is at point B, 3 by 2 to PA. Okay, so moment at point B has been calculated. Just remember that x is slightly greater than 0 means a minus a, yeah, x minus a is slightly greater than 0. It is a positive number. It is almost equal to 0. If we take power 0 of this number, it will be equal to 1. If we take power 1 of this number, it is almost equal to 0. So we will keep it 0. Okay, we will move further towards the next problem, which is problem number 108 from the exercise. Using singularity functions, write the equations for shear and bending moment for the beam and loading shown. So we will use singularity functions to write the expression for this beam, expression for shear force and bending moment. And part B, determine the maximum value of bending moment in the beam. So first we will write expressions for shear force and bending moment. Okay, remember that before anything we will calculate reaction forces. This reaction force at A is important for us, not at B. So if we take summation of forces in vertical direction equal to 0, this force has to be converted into concentrated force, which will be equal to 25 into 1.8. 25 into 1.8 becomes 45 kilonewton. So if you take summation of moments equal to 0, not forces, summation of moment at point D equal to 0 at this point, because here is an unknown RD which we do not need to calculate. So you can find RA equal to 62.5. I do not want to repeat this part. This is from statics. You can do it by yourself. What is important in this problem is we have to extend this load till the right. It should be right and close load. So we have to add upward forces of the same magnitude, upward distributed force of the same magnitude, 25 kilonewton, because we have added downward distributed force. Now these two forces, this force and this force, they are right and closed loads, and we can write singularity functions for them. So I will go towards the solution. Problem 5.108. RA and RD both are same. They are equal to 62 point, because this is a symmetric beam, so their reactions are same. We do not need RD in this problem. Okay. Diagram is here. At NA we have RA equal to 62.5 kilonewtons. Then at point B we have a 40 kilonewton force downward. At point C we have a 40 kilonewton force downward. There's a downward distributed load and an upward distributed load. Now we have completed this load till the right end. So I will write a complete load here, 25 kilonewton per meter. Here is RD and here is 25 kilonewton per meter distributed load. Okay, the distances are like this one is 0.6 meter, then 1.8 meters, and then then again 0.6 meters. Okay. First we will write shear force function. We have three distributed loads here, one at point A, then at point B, then at point C. We do not need to consider the last one for singularity functions. Okay. So why we don't need to consider the last one? Because when we write it is like x minus a. So for the last function, for the last load, it is x minus total length, and for the last point itself, x is equal to L. So it becomes the L minus L becomes 0. So the last point is not important for us. There is nothing on the right of this point, so it is not important. The concentrated load at the last point is not important. Okay, we have three concentrated forces, one at point A, then at point B, and then at point C, and two distributed loads, one downward and one upward. So we have to write singularity functions for all of them. For the one at point A, singularity function for concentrated force, singularity function of shear force for a concentrated load is minus P into x minus a power 0. For downward forces, remember that it is minus. So here at A we have upward load, so it will be positive 62.5 into x minus 0 power 0. Then minus 40, it is downward. X minus, it has a distance of 0.6 from the left end. So x minus 0.6 power 0. And again, this force of 40 kilonewton has a distance of 2.4 from the left end. So it is x minus 40 into x minus 2.4 power 0. Then there are two distributed forces. For a distributed force, uniformly distributed force, shear force function is minus W naught into x minus a power 1 for downward distributed loads. Remember that this is right and closed. That is why we have closed our loads till the right end. So minus W naught into x minus a power 1. Here it is minus, for this load of 25 kilonewton, minus 25 into x minus a. Here our a is 0.6 power 1. And for this force of 25 kilonewtons, since this is upward, we have negative sign for downward one. So for the upward one, it will be plus 25 into x minus its distance of this distributed load is 2.4. It is between these 2 points. Okay, the first term is x minus a power x minus 0 power 0. So x minus 0 is x, and x power 0 will be 1. So it becomes 62.5, and rest of the terms will be the same. 40 into x minus 0.6 power 0 minus 40 into x minus 2.4 power 0 minus 25 into x minus 0.6 power 1 plus 25 into x minus 2.4 power 1. This is singularity function for the shear force. Okay, for the bending moment, either we can integrate the shear force function, or we can write bending moment function again. We have three concentrated forces, 62.5 kilonewton, 40 kilonewton, and 40 kilonewton. So for all of them, the bending moment function will be like this: minus p into x minus a power 1. It is downward. For downward force, it is minus p. For upward force, it will be plus p. So for this upward force, 62.5 kilonewton, it will be plus 62.5 to x minus 0 power 1. Here, x minus 0 will be x, and x power 1 will be x again. So I will write it x like this. Instead of this, if we would have integrated this shear force function, so this term will be 62.5 x. So integration and the table values are same. Okay. Then this downward force of 40 kilonewton, so minus 40 into x minus 0.6 power 1, and this one has a distance of 2.4 from the left hand. It is minus 40 into x minus 2.4 power 1. These terms have been written from the table similar to this expression: minus p for the downward load into x minus a. A is the distance of the force from the left end in power 1. Instead of this, if we would have integrated the previous two functions, these two would have become like this. After integration, power 0 becomes power 1. Okay, the next function is for distributed load, downward distributed load and upward distributed load. For distributed loads, bending moment function is like minus w naught by 2 into x minus a power 2. For downward forces, it is negative w naught by 2. For upward forces, it will be positive w naught by 2. So for downward 25 kilonewton, it will be negative 25 by 2. So 25 by 2 can be written as 12.5 into x minus 0.6 power 2. And for upward force, it will be plus 25 by 2. So 25 by 2, again, it can be written as 12.5 to x minus 2.4 power 2. Instead of this, if we would have integrated these two functions, it will become like this. So the bending moment function is simply integral of the shear force function. If there is any separate bending moment applied in the diagram, we would add their singularity function here. So this is singularity function for the bending moment. This was first part of the problem. In the second part, we were asked to find the maximum bending moment. So for the maximum moment, its first derivative, which is equal to shear force, will be equal to 0. So we will keep shear force is equal to 0. The equation of shear force is equal to 0. So 62.5 minus 40 into x minus 0.6 power 0 minus 40 into x minus 2.4 power 0 minus 25 into x minus 0.6 power 1 plus 25 into x minus 2.4 power 1. This is expression for shear force. This must be equal to 0 to find the value of x where moment will be maximum. Now it is a singularity function. We cannot open these brackets very simply. So first we will check it in different ranges. The first range is between a and b when x is between 0 and 0.6. If x is between 0 and 0.6, if we keep x equal to 0.66 in the above expression, when x is 0.6, this term becomes 0, no problem. When x equal to 0.6 in this term, it becomes negative x minus 2.4, and we will neglect the negative terms. So this, if we neglect this term, this term will be omitted. Again, if we put x equal to 0 in this term, it will be, if we put x equal to 0.6 in this term, it becomes 0. And if we put x equal to 0.6 in this term, it will be negative. Any negative number in a singularity function, negative number in the singularity brackets, so this term, the term will be omitted. So this term will be omitted, it will be negative 0.6 minus 2.4. So all these four terms will be 0 if x is between 0 and 0.6. So we get 62.5 equal to 0. This is not possible. This is not possible. X is not between 0 and 0.6. What is the next range? Let us consider x is between these 2 points. X is between 0.6 and 1.8. Let us consider if x is between 0.6 and 1.8. Now, if we put x equal to 1.8 in the above expression, this may be possible now. 62.5 minus 40 into 1.8 minus 0.6 minus 40 into 1.8 minus 2.4 minus 25 into 1.8 minus 0.6 minus 25 plus 25 into 1.8 minus 2.4. Again, here are some terms, some of the terms where the number inside the singularity bracket will be negative. For example, here 1.8 minus 2.4 is a negative number, so this term will be omitted. 1.8 minus 2.4 is a negative number, so this term will be omitted. So here it is positive 1.8 minus 0.6, so we can replace them with the regular brackets. This one again, we can replace them with regular brackets. Okay, so x can be calculated from here, which will be 1.5 meters. So it is possible now. It is a positive number. Put this value of x in the expression of moment. For example, this expression, if I call it equation number 1, so put it in equation number 1. We can find the value of bending moment, maximum bending moment. M maximum is equal to M 1.5. Put x equal to 1.5 in this expression. It will be 62.5 minus 40 into 1.5 minus 0.6 power 0, sorry, power 1. Minus 40 into 1.5 minus 2.4. 1.5 minus 2.4 will be a negative number. Any negative number inside the singularity function, so this term can be neglected. We do not need this term. Okay, here minus 25 into 1.5 minus 0.6. Minus 25 into 1.5 minus 0.6. This is a positive number, so I have used a regular parenthesis for it. In the last one, sorry, we are not using this expression. I am putting values in equation number 1. This one here, if we put 1.5 here, it is negative, so we will neglect this term. If we put 1.5 here, it is positive, so we will consider this term. Minus 12.5 into 1.5 minus 0.6 power 2. And the last one, if we put 1.5 in this expression, in this term, x equal to 1.5, so it is a negative. It will be a negative term inside the Macaulay bracket, so it will be negative, means we will neglect it. This term does not exist if x is equal to 1.5. So this is a simple one. M maximum becomes, after calculations, it becomes 47.625 kilonewton meters. So remember that simply for singularity functions, if anything inside the singularity bracket is negative, we will neglect that whole term. If anything inside the singularity function becomes 0, so automatically the term is 0. So we must only consider those terms where the singularity function inside the bracket is a positive number. So I hope this was easy to understand. If there is any problem or anything to discuss, you can send me an email to discuss. Thank you very much.